Hello everyone, my name is Dongchi, and I'm really glad here that I can present our work at EC3 conference. I'm a postdoc from the Smart Construction Research Group from New York University of Dhabi. Today we present our work, Cyber Risk Identification in Construction with Language Models, the next generation. At the beginning, let me introduce you the background of our research. Today, 36% of construction projects face delays from cybersecurity breaches, a stark reminder that as we embrace Construction 4.0 and integrate smart cranes, cloud-based planning tools, and automated workflows, we're also inviting new cybersecurity vulnerabilities. As we can see, there are a lot of different accidents happen to the construction companies, which highlights 5 kinds of unique challenges in construction. Complex technology integration, fragmented supply chains, outdated legacy systems, phase-specific threats, and a general lack of cyber awareness. In short, digital gains must be matched by stronger defenses or we will continue trading efficiency for exposure. To comprehensively manage cybersecurity risks, the first step is to identify the risks that may arise across each project phase. A recent scoping review reveals a stark reality. Only 45 applications address construction cybersecurity, and just 3 are relevant to cyber risk identification. Existing methods like method threat modeling are predominantly manual and static, leading to time-consuming processes, potential biases, and fragmented solutions that cannot adapt to evolving threats. Therefore, automating cyber risk identification is imperative. Language models have become widespread since the 2017 introduction of the transformer architecture and have evolved into today's powerful large language models. Building on these automation imperatives, we led the use of language models for construction cyber risk identification last year. Although our study produced a relatively comprehensive list of cyber risks across project phases, it had some limitations. For example, it relied on small-scale models, used outdated data, and most critically, provided only partial automation, still requiring up to 6 hours of manual work to summarize the risk checklist and lacked any integration capabilities. Our new research addresses this gap by delivering an efficient, fully automated, and easily integrable solution. To bridge the research gap, our research pursues 4 key objectives. First, we collect the most up-to-date construction cybersecurity text data. Second, we fine-tune the advanced GPT-4o Mini model. Third, we evaluate its performance against various benchmarks. And fourth, we formulate a comprehensive phase-specific cyber risk checklist, which can be served as a new industry standard. Now let's explain our methodology. Here is why we picked the GPT-4o Mini model as our backbone model. Firstly, it is really cheaper per token compared with the GPT 3.5 Turbo, making it a budget-friendly choice. Secondly, it performs really good on various benchmarks, and it can process a really large context window, so it can process the entire project document in just one go. And thirdly, its streamlined design delivers sub-second latency, which is critical for real-time risk identification. Let me walk you through our methodology's key innovation, a 2-stage fine-tuning process. In stage 1, which is unsupervised fine-tuning, we feed the model a massive, newly collected corpus of the construction cybersecurity text, which is over 5.3 million characters. By working with the long text chunks instead of the isolated sentences, the model learns the broader context that is essential for spotting complex risks. Then in stage 2, which is the supervised fine-tuning process, we refine it using 1,630 carefully engineered question and answer pairs. These include both different linguistic styles of questions, which can mirror how someone might really ask, say, identify commissioning phase risks, or someone might say, could you please tell me the risks in the commissioning phase? By doing this, we adapt the model specifically for cyber risk identification tasks. For stage 1, the unsupervised fine-tuning process, we collected 48 up-to-date documents, which include papers, books, guidelines, published between 2022 and 2025. This ensures our model learns from the latest threat landscape. Critically, we process this data into one 133 contextual text chunks, each capped at less than 50,000 characters. Unlike the prior sentence-level split, our chunking approach preserves holistic context, which is essential for the model to grasp complex cybersecurity relationships within the document. This resulted in a rich 5.3 million character corpus. These chunks, formatted appropriately, provide the foundational domain knowledge for the model. We did the unsupervised fine-tuning process using the OpenAI's API. Moving to stage 2, the supervised fine-tuning process, we used 1,630 expertly crafted question and answer pairs built upon 326 core cybersecurity questions. Crucially, each question was rephrased into 5 distinct linguistic styles, encompassing both interrogative forms, for example, what risks exist in the design phase, and imperative forms, for example, identify risks in the design phase. This deliberate diversity in prompt engineering is important. It teaches the model to recognize and respond accurately to the different real-world user queries, significantly enhancing its linguistic versatility and robustness, which is important for reliable deployment in practical scenarios across all project phases. Our two-stage fine-tuning achieved excellent convergence. Stage 1 validation loss reached 2.05. Stage 2 significantly reduced this to 0.0156, which indicates the near-perfect alignment with target outputs. This progressive loss decay confirms the effective knowledge transfer. Now it comes to the model evaluation part. Let's look at how we evaluated our fine-tuned model. We crafted 30 targeted prompts by mixing 5 different question styles with all 6 project phases. Here are the prompts like, what risks exist in the design phase? Or the command, identify commissioning risks. We formulated the reference answers as indicated in the table, which conform to our previous study, as you can see in the table. We kept all model responses at under 50 tokens for 3 key reasons. Firstly, it creates a level playing field so we can compare different models consistently. Secondly, it mirrors the concise answer length in our fine-tuning data, keeping the model's behavior aligned. And third, it forces brevity, so field engineers get quick, actionable insights instead of the long-winded reports. To measure performance, we ran each model's output through 3 standard NLP metrics. Blue score for vocabulary and structure overlap, red score for content recall and precision, and bird score for deep semantic similarity. Together, this gives us a clear, objective picture of the accuracy and coherence. Here we present the results of our model comparison. We evaluated 6 models in total, including both smaller and larger model scale. We extracted the most relevant findings on the slide. Overall, our Stage 2 fine-tuned GPT-4o Mini model outperforms every baseline across all metrics and is the best model for cyber risk identification. With updated data, proper model size, and targeted fine-tuning strategy, our GPT-4o Mini Stage 2 model provides the best balance of capacity and optimization for cyber risk identification. Using the trained model, we again applied cyber risk identification to each phase of construction project, employing the same prompt terminology as in our previous study. The results for project initiation phase are presented in the paper and are more comprehensive than those in our earlier work, as you can see in the slide as well. Compared to the previous checklist with only 36 risk items, this study identified 57 items, thereby enhancing the comprehensiveness of the risk identification task. The time required to review and compile the list was significantly reduced from 6 hours to less than 20 minutes by involving just one person in the process. This increased efficiency is attributed to our newly fine-tuned model, which generates more cohesive and accurate responses that are easier to interpret. Furthermore, unlike our earlier GPT-2 model, the updated model can provide detailed explanations for each cyber risk item when prompted for longer descriptions. These advancements represent a substantial improvement in our risk identification process. Now let's come to the discussion part. Beyond risk identification, the checklist enables proactive mitigation. Project managers can prioritize controls before each phase. IT and cybersecurity teams can audit and harden existing protocols, and it doubles as training material, which fosters a true cybersecurity culture across the organization. Moreover, the model's reasoning extends to risk assessment and strategy formulation. By supplying project-specific variables, it generates threat likelihood scores and recommends tailored countermeasures, which powers the data-driven security planning. Deploying our solution is seamless and cost-effective. It integrates via API into existing platforms such as Procore and Buildertrend, with sub-2-second latency delivering real-time risk alerts to field teams. Importantly, it runs at an exceptionally low cost, just 0.15 per million input tokens, with monthly updates under just $1, democratizing enterprise-grade cybersecurity for small and middle enterprises across the construction industry. However, here are also some limitations. The dataset used lacks detailed project-specific information due to the difficulty of obtaining such data, which limits the model's ability to assess the unique cyber risks for individual projects. The study didn't evaluate the model's performance on a broader range of tasks, such as threat classification and detection or cybersecurity document validation, making it premature to conclude that the model can handle all risk-related tasks. Future work, thus, will focus on gathering diverse datasets to enhance the model's abilities, which are aligned with the company's specific needs and may include inputs and outputs such as codes, project network diagrams, or schedules. The final goal is to integrate this enhanced tool into the web or mobile applications, which offers an intelligent cybersecurity consultant for users without specialized expertise. Thanks, that's all, and we welcome any questions.